Transition elements form colored compounds, or compounds of transition elements are colored. But how? Compounds of transition elements are colored. How? Let us see the matter. Transition elements form colored compounds, or compounds of transition elements are colored. How? Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Here, all these elements are D block elements. D block elements. From these D block elements, these elements are transition elements. Transition elements or transition metals. D block elements and transition elements. This matter has been discussed in detail in the previous lesson. What are D block elements and what are transition elements? This matter has been clarified thoroughly in the previous lesson. In this lesson, we are going to learn transition elements form colored compounds, or compounds of transition elements are colored. But how? This is what we are going to learn today. Here, compound of scandium. Suppose scandium chloride, which is white in color. Then compound of zinc. Suppose zinc chloride. This is also white in color. Then copper 1 chloride or cuprous chloride. This is also white in color. Then copper 2 chloride or cupric chloride. This is light brown. Then ferrous chloride or iron 2 chloride. This is pale green. Ferric chloride or iron 3 chloride, which is brown in color. But the question is, how compounds of transition elements are of different colors? Here, this is the basic concept. Suppose this is a substance in which this is incident light, radiations. This substance absorbs these radiations completely. In that case, it will be black in color. For complete absorption, the compound becomes black in color. When the substance reflects completely, for complete reflection, the substance becomes white in color. But in this case, this is incident radiation. It absorbs energy partially, and when the substance reflects radiation partially, absorption partially, reflection partially, that is here partial reflection. In case of partial absorption and partial reflection, the substance becomes colored. Basic concept of substances to be colored. In case of compounds of transition elements, 3 points responsible. Responsible points. Point number 1. Electronic configurations of metal cations. Here, basically, partially filled d orbitals are responsible. Partially filled d orbitals are responsible to form colored compounds. Number 2 point, which is responsible to form colored compounds. This is presence of anions or ligands. Presence of anions or ligands is responsible to form colored compounds. Number 3. Point number 3 is absorption and reflection of light. Absorption and reflection of light, or absorption and reflection of radiation. Here, these 3 points are responsible to form colored compounds. Now, let us see how these 3 points are responsible to form colored compounds. Let us suppose the compound is iron 2 chloride or ferrous chloride, which is pale green. Here, iron, atomic number 26. In this case, metal ion is iron 2 plus. 2 plus. It means this ion has 24 electrons. Now let us write electronic configuration. 1s2, 2s2, 2p6, 3s2, 3p6. Up to 3p, there are 18 electrons. Then 3d, 4s, 3d6, 4s0, that is 18 plus 6, total 24 electrons. Here we see that partially filled d orbitals, which is responsible to form colloid compounds. Here potential energy d orbitals 1 2 3 4 5 d orbitals dxy dyz dzx dx square y square, and this is dz square. Here these 5d orbitals are of same energy, orbitals with same energy. This state is called degenerate state of orbitals. State of being same energy. This state is known as degenerate state of orbitals. Here, this is degenerate state of d orbitals. Now, these d orbitals contain 6 electrons. Electrons are distributed according to Hund's rule. 2, 3, 4, 5. Then, as paired, this electron distribution is according to Hund's rule. Now, role of anion or ligand. Here, anion is chloride ion. When these chloride ions come closer to the metal cation, then electron-electron repulsion occurs. Electron of anion and electrons in d orbitals. Here, electron-electron repulsion occurs, and as a result, energy of d orbitals increases in this way. 1, 2, 3, 4, 5. Energy of d orbitals increases. Here, electrons remain in the same state. It doesn't stop here. Now, these 5d orbitals is split into 2 groups in this way. Group of 3 orbitals, and here group of 2 orbitals. So 5d orbitals split into 2 groups. Group of 3 orbitals with lower energy are symbolized by T2z, and group of 2 orbitals with higher energy are known as easy orbitals. This splitting of d orbitals is known as crystal field splitting effect. Splitting of d orbitals is known as crystal field splitting effect. Due to the splitting or due to the crystal field splitting effect, energy gap is created between these 2 group orbitals. That is, degenerate state of orbitals breaks to non-degenerate state of orbitals. Orbitals with different energies are called non-degenerate state of orbitals. State of orbitals with different energies is called non-degenerate state of orbitals. And here, this energy gap is created. This energy is called crystal field splitting energy. This E is energy and this E is effect. Crystal field splitting effect and the energy created between these two group orbitals is called crystal field splitting energy, and orbitals go to the non-degenerate state from degenerate state. Now these 6 electrons occupy these orbitals again according to Aufbau principle. According to Aufbau principle, electrons will occupy first lower energy orbitals, 6 orbitals, according to Hund's rule 111, and according to Aufbau principle, lower energy orbitals 4, 5, 6. So now we observe that these 3 orbitals are filled with 6 electrons, but these easy orbitals are vacant. This vacancy of orbitals is basically responsible to form colored compounds. Vacancy of these orbitals is key point to form colored compounds. Vacancy of orbitals and this energy gap. Due to this energy gap and vacancy of orbitals, this ion can absorb energy, and as a result, electrons from lower energy orbitals shift to the higher energy orbitals, absorbing energy. In this case, this ion absorbs some radiations from visible light region, and as a result, these electrons shift to the higher energy orbitals. Radiations of visible light region, visible light, wavelength 380 nanometer to 780 nanometer. Radiations with this wavelength are visible light radiations. So when this ion absorbs radiations, some radiations from visible light region, and absorbing energy from visible light region, electrons shift to the higher energy level. At the same time, this ion reflects remaining radiations from the visible light region. Remaining radiations goes back to eyes. When remaining radiations from visible light region goes back to eyes, then this ion looks colored due to the partial reflection from visible light region. When this energy difference matches with the energy of the visible light region, then absorption occurs and electrons shift to the higher energy level in this way. 4, 5, 6. Absorbing some radiations of visible light region. At the same time, this ion reflects remaining radiation from the visible light region and the ion looks colored. So here the key point is vacancy of the orbitals and energy gap. And as a result, due to the energy gap and vacant orbitals, ion absorbs energy. At the same time, it reflects some radiations from the visible light region. Due to the partial reflection, this ion, ferrous ion, looks colored. Here, color of the visible light region is white. But when partial reflection occurs, then it becomes colored. That is, this is complementary color of white color. So this is complementary color. Pale green is complementary color of visible light region. That is, here responsible points are electronic configurations of metal cations, then presence of anions, and after that absorption and reflection of light. These 3 points are responsible to form colored compounds. At the same time, vacancy of these orbitals and energy gap, that is, splitting of the orbitals, is responsible to form colored compounds. Now let us see why scandium chloride is white. Here the ion is scandium 3+. Scandium, atomic number 21. Scandium 3+ ion contains 18 electrons. Electronic configuration 3d0, 4s0. Here 1s2, 2s2, 2p6, 3s2, 3p6. D orbital, which is completely vacant, but partially filled d orbitals are responsible to form colored compounds. Partially filled d orbitals. Here d orbitals contain no electrons, no splitting, no absorption of light. Here complete reflection occurs. Due to the complete reflection, scandium chloride is not colored. This is white in color. Again, copper 1 chloride or cuprous chloride. Here, copper, atomic number 29. Here the ion is copper plus. Copper plus ion contains 28 electrons. Electronic configuration 3d10, 4s0. 28 electrons. Up to this, up to 3p orbitals, 18 electrons, 10 electrons. So total 20 electrons. Here the orbitals are completely filled. Completely filled d orbitals. In this case, absorbing energy from the visible light region, there is no scope of shifting of electrons from lower energy orbitals to higher energy orbitals because 3D orbitals are completely filled. For this reason, in this case, complete reflection occurs. That is why this is white in color, copper 1 chloride or cuprous chloride. Again, zinc chloride. This is also white in color. Here, zinc 30. Iron is zinc 2 plus. It contains 28 electrons like copper ion. Same electronic configuration. 3d10, 4s0. Completely filled d orbitals. Here as well, there is no scope to absorb energy from visible light region because in this case, orbitals are completely filled. This is all about formation of colored compounds by transition elements. That is, transition elements form colored compounds, or compounds of transition elements are colored. The main reason is partially filled d orbitals, splitting of d orbitals, absorption of light from visible light region, and shifting of electrons from lower energy orbitals to higher energy orbitals. And as a result, reflection of radiation partially from visible light region. Due to the partial reflection, the compounds become colored. Thank you for watching.